Hi, I'm Aki Fujimura, CEO of B2S, and we're the managing company sponsor of the eBeam initiative. Welcome to the Fine Line Video Journal. Joining me today is Dan Hutcheson. Welcome, Dan.
Yeah. Thank you.
Yeah.
My pleasure.
It's great to see you.
I mean, we have fine line and fine cuisine, right?
Fine cuisine at the Flume Horse, yeah. Yeah, thank you. I saw you last when you were giving a really moving tribute to Gordon Moore, who passed away last year at the SPIE Advanced Lithography Conference. And how did you get to know Gordon Moore?
Through my father. I mean, you know, in those days it was a very small technical community, and so I got to know him through that, and then the stuff that we published, and you know, one thing led to another, and I get to meet him here and there and ask him about Moore's Law, because I'd asked my dad these questions, and he wanted to go talk to Gordon.
Your dad was Jerry Hutcheson.
Jerry Hutcheson.
Yeah, he's also a famous guy. Yeah.
He was a device physicist, and I'm an economist by background, so we had this nice kind of complementarity.
Yeah, that's really good. And I heard you say at other occasions about EUV that's happening right now, and I think you said EUV was a 30-year overnight success, which is an interesting way to say it. What did you mean by that?
Well, you know, it's interesting when you read the media right now, especially the stuff about China and the U.S., those battles and everything, and it's brought the general media in. They seem to think that EUV happened yesterday, you know, and it is an overnight success. And it's not, because I remember the first talk I saw on it way back in 1988 and at Xerox PARC, and Lawrence Livermore was giving a presentation, and I looked at this and I said, this actually might work because it has lenses. You know, you can do things like magnification correction, that sort of thing, that you couldn't do with proximity X-ray, which really was, even by then it was clear it wasn't going anywhere. And everybody was in this battle to figure out what the next generation lithography technology would be, which the last time we were in this quandary, it was with the move from projection aligners to steppers.
So wait, so you mentioned that you're an economist, and your dad was he's one of the inventors of one of the many ways that transistors were tried, right? At the RCA, I think, right? And so he was colleagues with all these other people who were trying to make it. Like, what's your technical background?
Other than what I've been in the industry, I've taken some extension engineering classes at Berkeley, stuff like that, and learned a lot. My dad's taught me a lot, and but you know, to me, the interesting thing was merging the economics with the technology, which my dad had all these figure of merit models for lithography, and the thing that kind of put me on the roadmap and was developing a cost model that took the yield equations, all that, and then calculated cost per good die. This is 1979, and it shows that the stepper is going to be the winning technology. And at the time, it was, you know, it was either deep UV projection or eBeam or X-ray proximity, and this clearly was the optimum technology. And so, and then after that win, I was looking for the next big win. You know, could I find a, you know, as we ran out of steam with the stepper, right, that what we'd get to. And it was clear the stepper had a long run with it, because we just keep switching wavelengths, light sources, that sort of thing, improving the NA. But eventually, as you know, that ran out at 193 dry. We tried to do 157 nanometer, and that turned out to be a big bomb, and all came crashing down, and then everyone panicked, and we made immersion work. And in the middle of all this, we're still working on EUV, among other things like multi-beam, eBeam for direct write, not for reticle writing, and other stuff like that. And in fact, multi-beam is where you kind of come into the picture as I recall, right? And
Yeah. So getting back all connected together with Moore's law and EUV, right? Before that, immersion coming into play.
well, I've written a lot of papers and chapters of books and stuff on Moore's law, and the interesting thing about Moore's law is the 2-year cadence. When you start to figure out how it fit into the economics of the industry, it fits into the depreciation cycle. Because people will upgrade stuff at a certain pace, right? So if you made it so that they had to upgrade everything all at once, the entire infrastructure, so it worked out that you really couldn't go much faster than once every 2 years. And at the same time, if you slow down the growth of the industry, which is in periods where we did see the slowing of Moore's law, like between 1978 and 1982, 83, we saw a really dramatic slowing of the growth of the industry. And then when we accelerate, the growth accelerates too, because it creates this natural replacement cycle. But then that's on the demand side. On the supply side, there's all these issues that we run into, whether, it might be materials or, we can't make the reticles, and remember the 1X lithography conundrum, right? Where looked great on paper, but you couldn't afford the reticles. You couldn't make the reticles work.
Yeah, 4X, the reticles being 4X the dimensions gave the mask makers holiday for a little while, but no longer, that's not
That was a pain. That was very painful, mask makers.
Yeah.
In fact, that kind of brings us to today's circle, right? The whole mask making piece of it, because it's a relatively small part, but it's incredibly critical, because without the masks, you can't make a semiconductor. Everybody focuses on the importance of the lithography tool, but the mask is even more important. And it's like the nail that lost the war, and the old story about the nail that wasn't put on the shoe, and the horse failed, and the cannon didn't get to the line on time, and the battle was lost, right?
Yeah, interesting. On Moore's law, one of the things that I think about often is how this is an industry that has to have many different disciplines, whether it's chemistry or computation or lithography, even mechanics. There's many different things that have to coordinate together. And if it wasn't for Moore's law establishing that there's this pace for every single element of it, like even if one element can be like much better, something else is not going to keep up, right? So it's important as a kind of a coordination, cadence. It's like, it's like a conductor, right?
Yeah. Although to a great extent, a lot of people see it. It's certainly slowing. And the problem I have with Moore's law is that everybody has their own definition of it. In terms of innovation, the innovation's definitely not slowing. There's demand for more innovation that continues. The cadence, the doubling of density, that's definitely slowed. But we still need more compute power. Now you start to look at the complexity of the process flow. And the other day you were talking about something that caught my eye, which was the X pattern.
Architecture?
X architecture. Tell me about that.
We did that work while I was at Simplex, and X architecture is kind of, in a way, now I look back at it, is a design version, a precursor to what we've been doing on the mask side with curvilinear masks. Curvilinear masks significantly enhance the wafer quality by having the mask shapes be curvilinear. The mask shapes had been written by VSP machines for a long time with rectilinear Manhattan axis parallel rectilinear patterns. And one exception to the VSP technology from the beginning really was that you could have 45-degree apertures.
Right.
Not just the rectangular.
So we began to think about doing a cross, but the design tools didn't accept it, right? So it never went anywhere, right?
So actually, at Simplex, we came up with the X architecture set of place and route tools that could actually do 45-degree routing, and many companies actually tried it and adopted it, and there were several production chips made with it, but on Simplex got acquired by Cadence, and Cadence decided to not pursue that, so it stopped being developed on.
So where are we today? You can do curvilinear, you've got multi-beam. Where are we today? How can I optimize the layers and maybe reduce some mask, especially in the metal interconnect?
Yeah. So now that masks can be curvilinear because of multi-beam writing instead of VSB writing.
And you say VSB, you mean vector shape beam?
No, it's variable shape beam.
Variable shape, excuse me,
yeah, what VSB stands for. And but that's the older technology, and now all the leading edge fabs have mask shops that have these new multi-beam machines. And because they have multi-beam machines, and multi-beams are basically pixel-based projection, just like TV screens now, all right? And because of that, any shape can be written on the mask just as accurately, just as quickly, and just as economically, right? And because of that, now curvilinear masks are manufacturable. Curvilinear wafer shapes are also manufacturable. And most people are not doing this yet, right? And where the world is today is they're taking advantage of curvilinear masks to make wafer production better, right? But what the world has yet to take advantage of, in my view, is the ability now to manufacture curvilinear shapes as target shapes on the wafer. Right? And just like what you were saying, the design tools, like the mask shapes are going through a transition, and that's forcing a change in the computational infrastructure on the mask side to make everything curvilinear. And the same thing, I think, is going to happen on the design side. And that would be the ultimate form of the X architecture that you were asking about, right? Instead of being restricted to only 45 degrees, because that's the only thing you could manufacture on the mask back then, now that we have multi-beam, you can do any shape on, so it's not just X, it's like arbitrary patterns. So I think that's where the world's going to go.
Yeah, and it makes sense because, what a lot of viewers probably don't realize is what you're describing is that, in a Manhattan architecture, you think about the streets of Manhattan, right? If I want to get from point A to point B, I have to do this or do that or maybe do something like this. I can't go straight there. And because of the RC delay in the copper lines, which is becoming more problematic as we make those lines smaller and smaller, and the barrier takes up more space, so you get more resistance. Being able to go straight to where you want to go could be a huge performance gain for the device itself, which is really critical in AI today.
Yeah.
To link all the way from the mask to the the thing that everybody in the world knows about AI is important, right? Well, AI is really critically limited today by the RC delay of the interconnect, and if you can shorten the distance by getting away from a Manhattan architecture, it becomes a huge advantage.
Yeah, I think so.
And that was kind of, when you were thinking X architecture a few years ago, you were going in that direction, but you were just ahead of the market. That's the...
The manufacturing limitation is now lifted.
Right.
And it's not just X, it's any arbitrary angle, and you can even do curvilinear shapes, right? So yeah, I think you're right. Show this distance between 2 points is not the Manhattan distance.
Yeah.
Right? Like if you can fly, that's better than going by bus, And I really think that will be a substantial savings. And on the design side, as you know, the clock speed is limited. Right? And clock speed is limited today more because of power limitations than because of frequency. You just can't clock it that fast because it would burn up.
Right.
And the power consumption aspect of it is also substantially better if you don't have to drive as far a distance.
Right. And that also gets helped a lot by backside power.
Yeah, yeah.
And, and separating the signal from the power interlinks, that helps a lot. And, which comes back to, that gives you more incentive to make the signal interconnect much more efficient.
And one of the things that we discovered during the X architecture is that clock routing is a big part of what's required for power consumption. And clock routing, you have to distribute the clock to the same spot. And instead of doing the Manhattan clock distribution, if you can have the main bus of the clock be diagonal, you save that 40% difference in distance, right? And so 20% savings in power or 30% even savings in overall chip power consumption was reported by people doing X architecture. People actually eliminated entire layer pairs of metal interconnect. Back in those days, it was 5, 6 layers or something like that. And they could eliminate one layer pair, one routing layer and one via layer that went with it.
Which is a huge cost saving in addition to performance.
Yeah. So people say that even just the X architecture restricted to 45 degrees was almost equivalent to at least half a node, maybe even as much as a node difference, right? So it's a software way, it's a design kind of a way to get a node's worth of an advantage.
Yeah, and you know what's really cool about that? You don't have to do a forklift upgrade of your lithography bay. And bring all these new tools in. So it actually brings more life to some of the older tools that are already installed.
Yeah, and even for the very leading edge, where maybe the transistor layers have to still use the leading edge, right? EUV now, high NA pretty soon, and hyper NA eventually. The upper layers can be done with the cheaper equipment, right? And that can be a substantial cost savings. And on top of cost, the power savings, the performance improvement, the area savings, and so on, right? I think it can be a substantial improvement,
So what else are you doing that's really cool and new that
because what D2S does is GPU acceleration for the semiconductor manufacturing industry, and we have both mask and mask synthesis or mask design aspects of what we work on. The world is changing to curvilinear, and in our world, where we only do things that are GPU accelerated, it's kind of an obvious thing for us to do is to make all the algorithms that are required to run on a computer be pixel-based instead of edge-based. So that's what D2S does. And, it's kind of like where image processing went. If you look at anything that people manipulate on TV or, PowerPoint, presentations, right? And PowerPoint presentations have edges in it, right? But how you display it on a GPU or, is all based on pixel-based manipulation. Right, like how you make a image sharpened, or all of those things. The image is sharpening the edges, but the sharpening mechanism is done using pixels.
Right.
And it's obvious to everybody else, right? But in electronic design automation, including in mask domain, the historical thing of many, 40 years, 50 years of doing it using edge-based, polygon-based manipulation is still the predominant way to do it, right? What D2S is working on is pixel-based version of that so that we can take the maximum advantage of the GPU as an accelerating platform.
So true computational lithography.
Yeah, it's computational
like
lithography.
at the recent NVIDIA, when they introduced the Blackwell, they were bragging about the computational lithography that made it possible. And what a lot of people don't realize is you think of a mask and you think of the pattern, the line that's being printed, and you think the mask looks like a line, but it doesn't. It looks like a noise, right?
Yeah. They, Jensen Wang in the announcement that talked about the Blackwell, he talked about cuLitho, which is the NVIDIA library for lithography, right? So, for NVIDIA, the use of GPU for semiconductor manufacturing or data preparation isn't a big market for them, right? But they make chips and they care about that. So they work on, accelerating lithography using CUDA, which is their programming language for.
Well, in fact, they couldn't make any progress if they weren't using GPUs to make GPUs. GPUs to do the computational lithography to make the GPUs.
Yeah, that loops back to the thing that we were talking about with Moore's law, right?
Yeah.
And all elements have to pace together, right? And it's in fact, I think, required for Moore's law to pace that computing paces along with it, right? So that we can design the next
generation
lithography or designs or whatever, right? Anything.
Right.
And using, this current generation of computers, using the last generation of Moore's law pacing, right? So, generationally, we use the previous generation to
design the next
generation, and that all of that paces together is actually an important part of Moore's law. It's an incredibly insightful thing that he came up with.
Yeah, it's really crazy. Although he was always embarrassed about it, and he just always said it was a wild extrapolation.
Yeah.
Well, of course, I one of my tribute I was saying it's the most important wild extrapolation in history. Because nothing else has created this kind of value.
Yeah.
The ability to draw from, start with silicon and get this computational complexity increase over time that is still going on.
Yeah, and it served as, like I was saying earlier, the cadence, it's the conductor, it's an automatic conductor, right? That paces the whole industry together. And, it's like, doesn't it amaze you that it actually does happen every 2 years? I mean, it's amazing, right?
Yeah, except for I think it comes back to what Carver Mead said, and that is that it's not so much about the technology, it's about all of us working together to move the technology forward. Yeah. If someone drops the ball, like you said, there's all this link in this whole chain. If someone doesn't make it, we stall. Yeah. And so everyone is pushing their own part or their own link of the chain to go to the next generation so we get forward. And to me, that's the most exciting thing, the most fun part about our industry is that we work as this really broad group, and all of us optimizing our own little piece, and somehow it all fits together. And like you say, it's amazing. Every couple of years, new things come out.
Yeah. It's the coordination and the collaboration aspect of it. To me, I really enjoy being a part of this industry because of that collaboration. Many different disciplines working together, and even competitively, we work together, right? Because there's this common thing that has to pace together and that has to keep going. So, I often talk about how I believe in, of course, being a capitalistic entity, D2S has to work on, increasing our piece of the pie, right? But to me, it's really important in any industry to work on growing the whole pie too. right? And in this industry, it's all the different pies, right? All of it together,
Right.
and we have to collaborate together to make that happen. And that's been happening, and it's reliably happening. There can't be that many parallels to this. Right, oftentimes, like your dad's days, military was a big driver of all that, right? Competing against the Sputnik, or right,
Right.
that was a big driver for why everybody had to collaborate together, even competitors. And
But at the end of the day, we're all trying to send our kids to college.
yeah,
Pay our mortgages.
yeah.
And that's what drives the innovation. And
Yeah.
the funny thing is John Chen, my good friend John Chen at NVIDIA,
Yeah.
he likes to say that it's not integrated circuit doesn't just stand for integrated circuit, it stands for innovation and collaboration.
Ah, interesting. Okay. Yeah.
And that's really our future going forward, I think.
Yeah. So what do you think is going to happen? Like, surely 2030, Moore's law's, still there. But 30 years from now, do you think it's going to, like, what do you think is going to happen?
I don't know. I mean, Gordon said no exponential is forever, but forever can be delayed. And, I've done 2 Scientific American articles.
Okay.
One was in '96 and one was in 2005, I believe. And both of them were spurred because people thought Moore's Law was coming to an end. And I wrote a piece about, well, no, both pieces were about, it's really about the people. And it's about our ability to innovate. And we're going to continue to try to innovate. It's just, the auto industry went through this in 1925. They hit a bottom in cost. I mean, the core of Moore's paper was that the density doubles and the cost is essentially halved because of the aerial cost of the silicon doesn't go up. And the auto industry went through the same thing, decreasing the price of the car through automation. Eventually they hit a bottom and the price of the car starts going up. And what happens is when you make that transition, you move from a cost down model to a value up model. And I believe that we're in that transition that from Moore's law cost down to a new model of value up that's still driven by innovation and collaboration.
Oh, interesting. Yeah. Well, thank you, Dan.
You're welcome.
It's really nice to talk with you. Yeah, it's great.
You're welcome. My pleasure.